Let's move forward in section 6.4 with some applications of implicit differentiation. All right, a couple of cool examples here. I'll probably make a separate video for each one. So let's start with example 4 here. Researchers have found a correlation between respiratory rate and body mass in the first 3 years of life. This correlation can be expressed by this function. And it looks like we've got some kind of a weird, almost a composition kind of thing where the R of W function is inside a logarithm. Okay, and then there's this variable W, and then there's this function in terms of W. Okay, where W is the body weight in kilograms and R of W is the respiratory rate in breaths per minute. Okay, and there's the source for this equation. So let's find R prime of W using implicit differentiation. Okay, so implicit because R of W is not by itself, right? So if we want to find R prime without trying to solve for R in the first place, we can just dive right in and find it implicitly. But I do want to make a note here that we're writing this as function notation. And so this notation, I just want to make a quick note that if we're trying to find R prime of W, R prime of W, that means that W is the independent variable. So we're trying to find dr dW. Okay, so we've been using that kind of notation all throughout this section, but since this one is presenting it to us in function notation, we're going to stay with that notation. But that same chain rule property is still going to apply, and instead of writing a dr dW to pop out from the chain rule, I'm going to use that R prime of W notation. Okay, so just keep that in mind. Let's go ahead and find the derivative implicitly. Let's just take the derivative with respect to W on both sides. So I'll go ahead and write that. I'm going to need a little bit of space here because I want to do some interesting things here. So let's write that as d over dW of both sides. So d over dW of this log of R of W. Okay, a lot of parentheses there, okay? And then just d over dW derivative with respect to W on both sides. Okay, and then as we go through and take the derivative here, we're going to have to pay attention to chain rule and also the derivative of a log. Okay, so recall that a lot of times we like using the natural log because the derivative is just 1 over the input times the derivative of the input. Okay, but just let me make a little note. Let's recall the derivative of any log. Okay, and I'll just kind of write down the general, if it's d over dx of log with any base a of, and I'll use u to really drive home. So suppose that like the u is a function of x. Recall that we did this in the past. It ends up being 1 over the natural log of the base times u, and then times du if there's a chain rule. Okay, so just recall that. We're going to need that a couple times as we're going through here. Okay, so let's go through and take the derivative. So the derivative with respect to W of log of R of W. So this is where we immediately need, we're doing the derivative of log base 10, right? The common log has a base 10 there. And so it's going to be 1 over natural log of 10. And then it's the u, which is just the full R of W function. So that R of W function is down there. Okay, and then the chain rule is times the derivative of the inside. And the derivative of R of W is just that, R prime of W. We don't need any kind of a dW thing to pop out because we're taking the derivative with respect to W. So remember that this R prime of W, that's the same as dr dW. Okay, so that side is good. Then on the right-hand side, the derivative with respect to W, that constant is just gone. And then we're going to get this negative 0.43. And then another derivative here. So it's log with a base 10. And so again, let's write this as it'll be 1 over the natural log of 10 with w, and then times the derivative of w. Okay, but since we're taking the derivative with respect to w, it would just be times 1. Okay, so that's done for there. Now we just want to make sure that we get r prime of w by itself. So we don't have to do too much work in that because it's only showing up in one location, right? It's only right here. So the only thing we have to do to get it by itself is multiply both sides of the equation by this thing over here, this 1 over natural log 10 r of w. If we just multiply both sides of the equation by that, it will cancel it, and then we're already done. Okay, so kind of cool. I'm going to multiply both sides of the equation by that thing, and so we're going to be able to write it as r prime of w equals, and I'll write all of this stuff in a couple of steps. So we have I'll put this negative 0.43 on top, and then we have natural log of 10 times w. Okay, and so what I'm doing is I'm multiplying both sides of the equation by the reciprocal of this. So instead of having a 1 over, it's going to be times natural log of 10 times r of w. Okay, so multiplying on both sides of the equation, and it would cancel. Okay, and then let's see, can we do any simplifying? It looks like since this is like over 1, when we multiply both sides by that reciprocal, looks like we can get that natural log of 10 to cancel. And then I'll write the final answer right here. We're going to have r prime of w equals, and we're just going to write this negative 0.43 and then there's this r of w that will be on top, r of w function that's on top. Divided by, and there's a w down there. All right, so we found the derivative r prime of w implicitly. Okay, and notice that a lot of times there's a mix of variables when we're done. So all the previous examples that we've been doing, you might have a mix of x's and y's in the answer. Well, here we have a mix of w and r of w's in the answer. But that's it. That's the derivative using implicit differentiation. So now let's explore the same process, sort of finding r prime of w, except let's first solve for r of w. So not implicitly. Let's find an explicit form. Okay, so let's solve for r of w. Okay, so let's go back to our original equation, and I'll just write it down again. We have log of r of w equals 1.83 minus 0.43 log w. All right, so we're going to solve for r of w, and that's just going to be pretty much a test in algebra abilities to try to get r of w by itself. So there's going to be a few different properties of logarithms that we're going to want to use to try to solve for r of w. Okay, so r of w, it's currently inside this log right here, so it would be really nice to try to switch this into exponential form at some point. But there's logs scattered all over the equation. So what I want to do is see if I can condense these into a single log. Okay, so let's get both of these logs on both sides of the equation. So plus 0.43. Okay, and plus 0.43. So I'm adding this log w to both sides. Okay. And then with these two logs right here adding up, now we can't combine those because r of w is different on the inside than w. But what I do want to do is start actually thinking about how can we put these logs together using properties of logarithms. So first things first, I'm just going to write down the log, the first one, r of w, and plus, and then in order to put these logs and actually combine them using properties of logarithms, I want to do two separate steps. The first step is I want to use that power rule to take that 0.43 and write it as an exponent on the w. Okay, remember the power rule, you can have any number in the front of your log and you can rewrite it as an exponent on the inside. So I'm going to do that. I'm going to write this as log of, and it's going to be w raised to the 0.43 power. Okay, power rule. And then over here, we just have this 1.83 left. Okay, now I'm going to use the next property of logarithms. If you recall that if you've got a sum of two different logarithms, as long as they have the same base, which these ones do, then you can combine them as a single log with the product of the insides. So we're going to apply that product rule now. So now we're going to have log of, and it's going to be r of w times w to the 0.43 power. Okay, good stuff. 1.83 over there. Okay, so we can't combine the stuff that's in there, but we don't really care now because remember, we're just trying to isolate r of w. Okay, so now that we have a single log equals a number, we can switch this into the exponential form. And remember that there's a base 10 right there. So to switch this into the exponential form, we would go, if you recall, it's the base raised to the power of the other side equals the part inside the log. So it's going to equal this r of w times w to the 0.43 power. Okay. And then last but not least, to get r of w by itself, we can divide both sides by that w to the 0.43 power. So we're going to get r of w equals 10 to the 1.83 divided by w to the 0.43. All right, so we've solved for r of w. Okay, so a little bit of a hassle there. We had to do some algebra tricks, but if we didn't know how to find the derivative implicitly, then we would have that process first. And now it does say find r prime of w. So we've got this. So let's continue now. It's going to be a little bit different because we don't need to do implicit differentiation. We can just take the derivative just right now, just right away. So let's write this. I'm going to rewrite this as we start. R of w equals, and I want to get this ready for the derivative. So that 10, it's a weird number, 10 to the 1.83. That's just a constant. And then that w, let's write it up here to the negative exponent, 0.43. And that's, the derivative is not going to be too bad. That's literally just going to be a power rule. So here we go, r prime of w. Okay, so that 10 raised to the 1.83, that's just a constant times the variable. Okay, so that's just going to stay 10 to the 1.83 power. Okay, and then here's where it's, slightly weird, but not too bad because this is just a power rule. The variable is w and it's raised to a power. So the derivative of the variable raised to any power is you multiply the power in front of the variable and then reduce the power by 1. Okay, and so even though it's a weird decimal thing, we still do the same thing. So we need to do negative 0.43 minus 1 is negative 1.43. Okay, and then that's pretty much it. Let's go ahead and clean this up just a little bit, and we can write this as r prime of w equals. And so how should we clean this up? Looks like this 10 raised to the weird power and then times that negative 0.43. I don't really want to type that all in. I'd rather leave it kind of exact. So let's just write this as negative 0.43 times 10 to the 1.83. And then since that W is to a negative exponent, let's go ahead and put that back on the bottom. Whoops. So that'll be W to the positive 1.43 when we put it back on the bottom. Okay, there we go. We've got R prime of W. So here's where I want to get a little bit philosophical and actually show you something really cool. Let's go back to our previous result. Okay, we found R prime of W in two different ways. In part A, we found it implicitly. In part B, we solved for R of W and then took the derivative of R of W directly. And look at these two results. Why do those not look the same? If this is a legitimate process to find the derivative implicitly, they should be the same, right? Well, you may have been noticing all throughout the course that if you're using derivatives and different kinds of techniques, you might get a slightly different looking answer, but it's actually algebraically equivalent. And that is the case here, because let's think about this. What's the main difference that you're noticing? Well, in the first one, notice that R prime of W is written, and there's an extra R of W function right there. Okay, so I don't want to like circle it and mess this all up and how nice it looks, but this R of W function right here is not present in the other one. So let's actually see what would happen if we take this and replace that R of W function with the explicit version that we found, right? We did all that work with the log properties to get R of W by itself. So we did all of that work, and R of W is actually this expression, 10 raised to the 1.83 divided by W to the 0.43. So let's take R of W and let's go up to our part A answer and plug it in right there and see if we can do some algebra to manipulate it to get it to look like the derivative that we got in part B. Okay, so let's try that. Let's go R prime of W equals negative 0.43. And instead of R of W, I'm going to plug in that expression there, 10 to the 1.83 power over W to the 0.43. Okay, so that is R of W that we solved for earlier, and then this is all over W. Okay, let's clean this up a little bit because now we've got a fraction inside of a fraction, so remember that we usually clear that by multiplying the numerator and the denominator by that denominator. Okay, so when we multiply this onto the top, it's just going to fully cancel. And then when we multiply it onto the bottom, let's see what we get. R prime of W equals, so on the top, all that's left is going to be this negative 0.43 times that 10, negative 0.43 times that 10 to the 1.83. And then in the denominator, we've got W times W to the 0.43. And so there's like a little 1 on that W as an exponent. And so when you multiply, the powers add up. So that's going to be W to the 1 plus 0.43, which is 1.43. And hey, how cool is that? That is exactly the same answer that we got when we first solved for R prime, or for R of W before taking the derivative. Okay, so yeah, that implicit form, it's definitely true, but we didn't know what R of W was. Okay, but over here we solved for R of W, now we know what it is, and we can show that these two are equivalent. Okay, so awesome stuff there. We're pretty much just doing some fancy manipulation with some function, not necessarily answering any extra questions about it, just seeing if we can actually work with some strange function, trying to find the derivative in different ways. Okay, pretty cool stuff. I'll go ahead and make one last video to pick up on example 5.